Hey,
What?
I'm going to share my screen. Both Andrew and I have got PowerPoint presentations to give. Andrew is another one of our team members on. Right now, we're building the digital camera for. Well, it's called the LSST camera for the VRO, which is. I'll get to that in a minute. Lots of in the last year, lots of renaming as other people in the world get involved. But Andrew's going to talk about the work he's been doing with our CCDs and our camera and what's going to happen when what they've been able to show what's going to happen with when we actually get the camera up and running. And Andrew's done amazing work in our lab to simulate that. Well, actually, it's a couple different labs that he's worked in, but that's kind of what drove me to want to come up and talk to you guys is that it's really fun to see Starlink go overhead at night, but the ramifications of something new and interesting to see is quite detrimental to what we're doing. Andrew will get into that. My talk is I'm going to share my screen now. Hang on. Which one am I doing? Uh-oh. Hang on. Here we go. Can everybody see my PowerPoint?
Yep.
Yep.
You don't see my email?
No, it's
Okay,
a really
good.
big picture of a telescope.
Yep, that's the Vera Rubin Observatory, a rendering thereof. What used to be called the LSST Observatory is now called Vera Rubin Observatory. It was renamed, and we'll get to, if you guys don't know who Vera Rubin is, we'll get to that in a second. A very famous and trailblazing female astronomer. And then a couple of different name changes. What happens when you go for another round of funding in our government, people get involved and things start getting renamed. But still the same purpose, same, just we call it different things. All right, go to the next, there we go. This slide shows the team that is here at Stanford at SLAC. SLAC is a national, a U.S. national lab. You see my cursor? So there's a picture of me.
Yep.
There's a picture of Andrew. Every single person in this picture is extremely important to the project. The project runs very lean as far as people go. And so it's amazing how much gets done with the few number of people that we have. So here's the next slide. Here's a rendering of what is now called the Vera Rubin Observatory. This observatory over here is going to be the calibration and facility that we're going to use to calibrate the main telescope. It's on top of a mountain. We'll get to, I think, the next slide. Well, the next slide is, if you don't know who Vera Rubin is, let me digress a little bit. I will certainly put this presentation up for people to go and grab it. This is also being recorded, so you can go back and grab it. But we'll make sure that the information that we have here is able for you guys to review if you want. Vera Rubin, a very important astronomer. Big thing is that she had to fight through lots of gender discrimination. She had to raise a family. As Andrew will attest, it's not easy to have an important job and a career path as she did, and absolutely be a family member too. She proved the existence of dark matter, which is fun, you know, that's amazing. And the powers that be thought it was very important that she get honored, and I totally agree. So this is what the observatory is now named. The camera is now called the LSST camera at VRO. And instead, a year ago, the whole project was called LSST, and that stood for, what did it stand for? Large synoptic scanning telescope. Now the acronym's been changed to a legacy survey of space and time. Virtually the same. The idea is that the observatory is going to catalog the southern sky on a continuous basis for a 10-year period. It's a methodical investigation of an area. In our case, it's the whole southern sky. And the idea is to capture in time the changes that happen and to catalog this survey for everyone in the world to be able to use. That includes you guys. The data will be available for use once we start getting data. And the amount of data is going to be incredible. We'll get to that later on in the presentation. My presentation got a lot of good little, this was kind of a year ago. The observatory, the dome was had not been put on yet. The dome is pretty much put on now. But everything as like with everything else, the work at the on the summit is been closed down, and we're not quite sure. I can tell you, I got good news for you. I'm going back to work on Wednesday. So things here are starting to move forward to try to get back to
normality.
We are about, I don't know how many people we got. Maybe 25 people involved in putting the camera together, and this week and for the maybe about the next 6 weeks, we're going to be limited to one person on site a day, and there's only been 4 people that have been approved to come in and help. We're trying to get what I'll describe it in a second, the cryostat, which is where all the camera elements are housed. Try to get that into an operating position so that scientists like Andrew can start doing characterizations of the whole focal plane. So moving on, that's where LSST is located. It's in the Andes mountain range of Western Chile, right outside a town called La Sirena, which is a place where I'll be spending a lot of time sometime in the future when Americans are actually let back into Chile. Right now, that can't happen. Move on. Another picture you can kind of see, it's at 8,700 feet, which is not the highest mountain, but it's for what we're doing, this was the best location. So moving on, I'm going to describe what does it take to build the observatory with the world's largest digital camera. It takes these things. It takes an 8.5 meter mirror. It takes a 3.2 gigapixel camera, a 35-ton telescope assembly, a 10-floor building. It's huge. The data center is world class. Can't say it's the largest one, but I think it's going to be real close. And then obviously, in my opinion, it takes the people. So going on, what's the objective and how do we go about having a legacy survey of space and time? Well, it boils down to a volume of universe per unit observing time, which means what? Well, and I'll get to this in later slides. It shows you how much of the sky. It's 3.5 degrees of the sky at any one time that we take an image, and we're going to be doing two images, two 15-second exposures continuously. It's a 30-second exposure time within about 37 seconds. So we take an image, we have to take a couple seconds to download that information to the center. Then we take a second one of this at the same location, we download it, and we slew to the next location. We have a slew rate of about 5 seconds. If you can imagine a 35-ton telescope assembly moving 3.5, exactly 3.5 degrees to the next motion is an incredible feat. It's very complex. And it's gonna be fun to figure out how close we can actually get to it. So we have some, kind of getting to the point of the talk with Andrew. These are some of the observing strategies that we're going to be employing with the LSST. The primary goal of the LSST or the VRO is to detect change over time. And as you can see, I've put in what the objective is. And then at the end of them, this is where Starlink becomes an issue. Because as you'll see with Andrew, when we have hundreds of satellites, little mini satellites that are big reflectors in the sky going through an image, it makes it tough for us. And so we can go through this, but I'm kind of limited on my time. Like I said, the presentation will be available for further review if you want. Going on to the next screen. This is the mirror design for the telescope. 3 basic mirrors, 1, 2, and 3. And it makes for a super compact telescope assembly. So here's a depiction of the focal plane. And you can see with a 3.5 degree field of view, we can actually put 7 full moons inside the focal plane for every image. That's how much sky we see in 4K video quality. Here's a rendering of what the telescope, the TMA and the dome assembly is going to look like. Thing to pay attention to is, let me get the cursor over here. That's the size of a pretty big dude. So you can kind of see how big this thing is. It's huge. So going on, here's a rendering of the whole observatory. We have the TMA, 350-ton TMA. We have the mirror coating facility down here. So the mirrors can come off and get recoated as we go through time. Because this is located on top of a mountain, which doesn't really have a big road that goes up to it. It's remote. And so it's really kind of a fully contained facility. We have a machine shop, we've got the control rooms, we have the camera clean room. If the camera has to come off or when it arrives, it goes into this clean room. And we've got all the refrigeration, all that stuff is all mounted up in here. So to give you a little bit more.
You know, you're going out. If you're going out, go out.
Poor Trevor. Here's one of my buddies that's helping with the building of the whole telescope. This is Margot Lopez. She put together most of this presentation that I'm giving earlier, a couple years ago, maybe a year and a half ago. But I want to give her credit for the work that she did in saying thank you. She loves corgis, and you guys will find out what I mean here in a little while. But you can see that here's Margot in Spain doing a review of what is called the TMA, or the Telescope Mounting Assembly. Oops, let me go back. I just hit a button and I wasn't supposed to. Anyways, you can kind of see how really big this is. This is a colossal facility. And here's Margot standing on an adjacent hill, and you can kind of see this was taken end of last year, I think. Maybe not, I don't know, but you can see where they're putting the panels on the dome. They weren't able to finish that this year because of the pandemic. The dome is put together by Italians. The TMA is put together by, I believe it's Spanish, and everybody had to go home. And hopefully soon we get to go back. That would be good. Like I said, I get to start on Wednesday trying to get the thing to start running again. All right, nerd alert, nerd alert. I won't really go through too much of this data. Once again, we'll do a couple of things. What would be good? The imaging system is 3.2 gigapixels. Readout time is 2 seconds. Pixel pitch is 10 microns, or 0.2 arc seconds. Let's see here. What else would be? Well, anyways, like I said, this is all going to be reviewable. Estimated counts for per data release is about 18 billion. Galaxies, planets, whatever you want to take a look at. Next slide, please. So here's another one of our strategies. How is VRO going to help in the discovery of dark energy? Short answer is dark energy is tricky. It isn't measurable as a global thing. That drives evolution of the universal scale and function of time. So an aggregate analysis of data will contribute to the understanding, which is why we're doing a legacy survey. And once again, I won't go through this too much because it's better to review at your own pace. So the next slide is to show you the scale of each one of our images. So each one of the yellow circles contains 10 million galaxies. We will observe half the sky, the southern hemisphere, 1,000 times over 10 years. There's 20 terabit of data per day, and that's 15 pentabit database at the end of the survey. That's numbers it's hard for me to understand. Approximately 40 million objects will be cataloged by the survey, more objects than humans on the Earth by a large number. And the enormity of the galaxy catalog combined with an exquisite understanding of the systematic effects will open a new window on our understanding of dark energy. All right, so now I'm going to get into the part that Andrew and I work on for the observatory, and that's the camera. Besides having a really good telescope, you need a camera, and we're building a pretty good one. But first, why corgis? Well, what's the best way to say it? Margot loves corgis. So, and in a way that, you know, she just has to kind of get corgis into everything. And you'll see what we do. If in your, on your Zoom screen, if you, every time you see a corgi, if you can raise your hand and participate, that'd be awesome. So there's a little function at the bottom of the, of your control panel window, and you can raise your hand or put it in the chat or something. All right, let's go. So here's the construction of the camera. It's, in my opinion, very classically designed. We've got lenses, we've got a shutter, we've got for doing astronomy, you need filters, so we have a filter assembly, and we have all the electronics that's needed to run such a camera. Right now, like I said, I am working on getting the cryostat operational. Cryostat is where we house the CCDs, the actual camera elements. And so here's a nice overview. What makes the LSST camera so impressive? It's the world's largest digital camera ever constructed. It's 3.2 gigapixels in image. It has a 640 millimeter focal plane and is flat to plus or minus 10 microns, which we have measured, and it is actually about half that. We did really, really fine work. Andrew was very much involved in making sure that all of the CCD sensors on each one of the, what we call RAFs, R-A-F-T-S, RAFs, which contain 9 CCDs each. Andrew was very pivotal in making sure that we get all of those put together and we get them measured, and we understood that before we ever put them in the cryostat for the actual camera. Oh, there's a little buddy. The camera itself is about 5.5 feet in diameter and about 12 feet long. And if you are familiar with sports cars, that's about the size of my 360. So if you kind of figure, here you got a Ferrari, you're going to put it on a telescope. That's how big it is. That's just the camera. It's huge. Oh, more corgis. So here's why we're using corgis. So if we use a standard US mailbox, which can estimate the size of a corgi puppy, it's about 0.75 cubic feet. So moving on. Oh, there's another corgi. Anyways, that's a rendering of a side view of the camera. You can see on the right-hand side here. Hello, buddy. This is the outside lens. Here's what we call the utility trunk, where all the control electronics and systems and assemblies are located out here. The actual camera elements are located back here. And I just switched over to the next screen before I was ready, but anyways, it's about 240 corgis can fit inside the camera. That's how large it is. So moving on, we're going to camera resolution. And if we go to the next, talking about how close do we get the actual camera elements to each other on the focal plane itself. Here's a depiction of cars that are 1 inch apart. I actually experienced this kind of parking arrangement when I was in London last year. It was amazing. We don't have that kind of problem here in California, but it's close. We're more like 6 to 8 inches, but moving on. Here's a picture of us starting to build what we call the focal plane, putting the CCDs in. And this is the actual grid assembly that all of the camera elements fit into. And so we have one element here. You can see it's got 9 CCDs on it. We have another one. These actually are our engineering units we use to practice and to learn how to put these actual elements into their final resting place. And here we go. Here's a picture of the CCDs going in for real. The couple of different manufacturers of the CCDs. The ones you see with the black outline here, they're made by Teledyne E2V in England, I believe, 90% sure of that. The other ones are a company called ITL down in Tucson, Arizona. But you can see on the left-hand one where you can see how much space there is when we're bringing another element up into the body. The space between these sensors is spec'd out at being plus or minus 250 microns from edge to edge. There were many times when the spacing became less than 50 microns. And a raft installation could take anywhere from 4 hours. And we thought that was amazing. We just would go in, put it in, be done, and go on for the next day. Or it could take us 3 days when things got to be a little tight. All right, going on to the next. Here's a picture that we finished putting all the elements into the cryostat earlier this year. These are pictures where you can see all of the CCDs in place. One picture on the bottom shows you the machine vision cameras that we used that helped us measure how close we are if we're going to run into anything. And because it's really hard when you're pulling something through a hole and you get 250 microns, which when you get used to it, you go, well, that's a lot. That's no problem. Except when it gets to be 10 microns and 20 microns, it's nice to have the machine vision there saying, hey, we got to move this thing a little to this way and a little bit to that way. So another scientist, Andy Rasmussen, was pivotal in making sure we could see what we were doing. Next slide. All right, so start talking more about camera resolution. One raft, one element, has 9 CCDs on it, which if you were to broadcast them all at once would take 18 4K televisions to actually display, which is equivalent to laying out TVs on 4 king beds. And there's what it looks like, the full depiction. We got 21 rafts, which would be 378 4K TVs to try to produce the one image we would take. And so here's a good picture. This is one of the camera elements. Oh, hi, buddy. In its transport rack. This is kind of what we used to walk them around the lab with. And here's a picture of Margot taking a picture of a raft. This is going into, I think this is going into what's called the commissioning camera. The commissioning camera is a 1 raft camera that will be put onto the telescope itself to categorize and learn how to use the telescope. Not so much, well, it'll be taking pictures of real data, but it's a 1 element camera instead of a 21. More talk about camera sensitivity. Maybe it could be more relatable. If we were to light a candle at SLAC in Palo Alto, California, or Menlo Park, it would be observable 10,400 kilometers away in Patagonia, Chile. That's the level of sensitivity the camera has. So kind of getting on to the end of my talk, so Andrew can get to the Starlink one. What makes a LSST camera so impressive? You can fit 240 corgis in it. You can cover half a basketball court with 4K televisions to display one raw image. You could see a candle from Stanford to Patagonia. And I'd like to thank Margot and Kevin Reel, Tony Tyson, the main dude, Aaron Rodman, and all the guys at Slack to help put this together and get me a part of an amazing, amazing project. So thank you. So with that, I would like to introduce, here I'll stop sharing my screen. I would like to introduce Andrew Bradshaw. Andrew is one of the scientists on the project, and he has been working on trying to find out and figure out what's the ramifications of on our camera to Starlink, because there's been already been a lot of data and people saying, you know, this is not good, guys, it's not good. So Andrew's been doing a lot of work in the lab, and I wanted to bring that to your guys' attention so that you are fully informed when you make your opinions about what's going on with Starlink. So Andrew, I hand over to you.
Andrew, before you talk, I think that one or two questions have come up, Boyd, during your talk.
Oh, okay.
Susie, do you want to turn on your microphone and articulate your question? Can I?
Oh, in a minute. Right. Can you hear me?
Though.
Right. Okay. Well, it's not. Why is it the telescope that's refrigerated or the camera, Boyd?
Oh, very good. I'm kind of the guy that's in charge. I don't want to say in charge, but I'm the guy that's responsible for refrigeration. The uniqueness of the camera that we are building is that the CCDs need to be cooled. Like this is standard stuff for these kinds of camera elements to a temperature of -130 C. That gets all the grain boundaries nicely packed together, and the ability for the CCDs to see very faint light and very faint energy is maximized. The uniqueness is that all of the electronics that are needed to actually operate the CCDs, power them on, turn them on, get the data out of it, give us all the feedback on how the sensors are actually doing, are all installed in a big, huge vacuum chamber. And so the electronics have to be cooled also, and they have to be cooled to somewhere about -40 C. So we have two separate refrigeration systems. One's cryogenic, it goes down to -130 C, and the other one's a real standard refrigeration system, pulling that heat energy away from the control electronics.
I think we had one more question. We had a question from Kevin about whether we use.
Yep.
Go on, Kevin. Do you want to ask it?
I assume that with the number of observations you're able to see, it'll be with the depth of field, you'll be able to see very faint rotations in the galaxies then? Better than we have with current telescopes.
I believe that's a very good observation. Andrew might want to add to that.
Yeah, actually the time scale for like galaxy rotations is like hundreds of thousands of years at the very like minimum. But with surveys like the LSST, we can kind of watch our own galaxy rotate. We can watch stars orbit the center of the galaxy and actually like kind of trace them back in time and figure out how the Milky Way was composed of all sorts of other objects. So yeah, we will see motions of galaxies, but only our own, not really so much of others.
Thank you.
I think Boyd has left us. I've got a couple more questions people have put up for Boyd, but perhaps we'll come back to those at the end of Andrew's talk. So Andrew, if I give you the, I've got to give you host status, haven't I? which I've lost the, there we go. But Andrew, we can't hear you.
Of course, yeah, I muted myself, sorry.
Right, okay, that's better.
Okay, yeah, you guys can see this?
Yes, we can.
Okay, now this is another critical test here. If I click present, does this work? You can see, okay, cool. All right, so, seems like we're working. So yeah, thanks Boyd for the excellent introduction. I'm glad he impressed upon you how amazing the LSST survey will be. It will be fantastic. It will be, as it's now officially in the title of the survey, it will be a legacy for years and years to come. It will be, you know, in the first 6 months or so of observation, it will actually collect more data on the sky than all of the previous history of all of the instruments and telescopes. So that's the amount of data that we're talking about, and so it'll be legendary for sure. And so it's really a privilege to be working on this project, and a privilege to be working with Boyd. He's such a great guy. I can't wait to get back in the lab with him. But yeah, so the main point of my talk today is Sudden StarLink Syndrome, which is kind of a joke on the current situation. But you know, of course, it's not a laughing matter. I hope everybody's doing well. Yeah, or simulating satellite streaks in sky survey sensors at SLAC. Sorry, I can't help myself sometimes with all the alliteration. But anyways, yeah, and there's a lot of people to thank. People who have directly influenced my work and my history include my advisor, Tony Tyson, who's one of the guys who dreamed up the LSST survey. Aaron Rudman, my current boss, he works at SLAC with Boyd and I, and he's a great guy in charge of the camera. Homer Neal, he's the guy on the ground floor doing a lot of the hard work with rafts, turning knobs and taking data. And Adam Snyder, he's a grad student that I'm helping, and he's helping me as well. And of course, Boyd. So just a little bit about me. I was born in Turkey and raised in Texas. I got an undergraduate in physics from Texas A&M, which was a nice in-state school, not too far from home, but just far enough. And that's really when I got into astronomy as a possible career. I did a senior thesis in astronomy when the A&M physics department was just hiring astronomers finally, and they got someone. I was like, oh, can I please work with you? Like, you know, you don't even have to pay me. Like, I'll just, you know, give me a project. And that's how this all got started. So I liked it so much, I applied to get a PhD in physics at UC Davis under my advisor, Tony Tyson. I studied a topic called weak gravitational lensing. It's a fascinating phenomenon in the sky where light rays get bent around massive clusters of galaxies and things like that. And so they magnify and distort the background images of galaxies. And I could talk about that for days, but that's not what we're talking about today. The LSST CCD camera studies are really what set me down the current path that I'm on. And that all took 8 years. So, you know, it took me 8 years to get a thesis done, and you know, I'm proud of it. But you know, that's a little bit longer than they do in England there. But I had I like to think that I had such wide-ranging topics in my thesis that it just took that long to complete. But anyways, towards the end of that, as I was continuing my research, there was the need to help the LSST camera in an effort to build and clean and some of the CCD parts, some of the camera parts. And so I volunteered to do that, and they officially hired me last fall. I'm very excited to join the team at Stanford and SLAC building the LSST camera. And just around the time that the camera focal plane was fully constructed and my job was, you know, my first job was complete, we had a baby girl. And so I have a 3-month-old just sitting here next to me, and I apologize for any cute outbursts that might happen, or if I, you know, am distracted and saying, oh, are you doing, you know, saying cute things to my baby. I also have 2 dogs, and so apologies for any, you know, in-home noises. And this is just a picture of the LSST focal plane partially completed, and I'm sitting under it. And so it was, it's kind of nice actually. This picture here was taken around 7 years ago when I was visiting at Oxford. They have a camera lab there that we were allowed to tour, and they had the 3D printed model of the rafts of the LSST. And I thought it was so cool to have a raft, you know, in my hands, and like, wow, this is going to be like, you know, 1/20th of the camera, and just you know, feeling kind of like the power of this, even of this like 3D printed model in my hands. And here, you know, 7 years later, I get to kind of sit under it and look at this amazing camera that's being built and tested here in California. And so, yeah, I just feel really privileged to be a part of the team. As I said, my whole journey started at UC Davis. We had a little optical setup on a table that simulated the LSST. So as Boyd was showing, the LSST is this magnificent telescope and camera combination on a mountaintop in Chile. We kind of simulate that in a laboratory in order to get a handle on how things might look before the survey even gets started. And so we have here our CCD lab at Davis, which is a unique facility that takes CCDs that will go into the LSST. We put them in a cryogenic dewar on the left. And the cryogenic means that we're constantly cooling it. As somebody was asking, you got to cool these CCDs down to about 200 degrees below zero and Celsius. And, or sorry, the coolant is around 200 degrees below zero Celsius, but we keep the camera at about minus 100. And you can see actually a little puff of vapor coming out because we just recently filled the tank for the camera, which was an annoying thing to do for 8 years, but it was necessary for the science. And in the middle, you can see this little black cylinder. This is a mock-up of the optics of the LSST, and this is the ray path is shown on the bottom here, where you can see the green. For instance, the green light rays come in through here, which is the half-silvered mirror, bounces off an annulus. This is a side cut through a donut. It's a donut mirror, just like the LSST will be. It bounces off the outer edge of the donut, bounces again off this mirror, goes through some optics, and then comes back to the CCD. And as you can see, it doesn't actually magnify very much. It's kind of what we call a re-imaging setup. And so what it does is it just looks at whatever's at the focal plane here and just basically reproduces it, photocopies it over here, but with this very special beam that the LSST will have. And so we can study how the light will bounce around and then end up in the sensors. And so studying the sensors was the main thrust of my PhD research when all of the Starlink went down. Here you can see my advisor, Tony Tyson, in the laboratory with a different colored dewar. We have two different flavors of dewars with two different types of CCDs that will go into the LSST. And so yeah, that's what it looks like in person. And I wonder if I can get that going. Oh no, there should be a video here. There we go. Okay, there's the button. And so probably no human, maybe someone lucky enough will get to look down the barrel of the LSST, but this is looking down the barrel of our little optical mock-up of the LSST. You can see we're imaging this little Air Force target that, you know, kind of tells you the resolution and has the features on all scales. And so this is kind of what it looks like to look down such a weird optical system. It has that cut out in the middle, as you can see, but it focuses, it re-images those whatever we put on the other side of this optical system very precisely and in the way that the LSST does. Okay, dogs, quiet, please. I'm sorry. Okay, no, I'll put you inside. Sorry. Anyways, so we can quiet. Okay. Yeah, so we can take a little disk of stars and then re-image it onto a sensor and move it around 1 micron at a time. And we've taken billions of little spots in the laboratory to mimic the billions of objects that the LSST will see. And then finally, we can measure these things in the laboratory and get all sorts of interesting science out of it. So we do little spots, big spots, galaxies at high resolution, lower resolution. This is just the kind of thing that we're studying to use, I could skip this slide, to study these CCDs. And this is what a CCD looks like when you scale it to plus or minus 0.1%. And this is, you just project a flat, illumination onto a CCD. And this is what you see at 1/10%. It's pretty ugly. It's got little scratches up here. It's got this like little, I don't know, like variation in like absorptivity perhaps of the silicon or something like that. But you can also see these faint little tree rings here. I don't know if you guys can see that on your screens, but there are these little arcs that go across here as well. And I'll show those in just a second as well. But at the edge, you can see it actually gets darker. And this isn't just like I'm, vignetting or cropping of the image or anything like that. It actually gets darker at the edge of the CCD. And so I don't know if some of you guys are amateur astronomers yourself, but there's certainly these types of effects happening in everybody's sensors. But this is the kind of thing that might be a problem for the LSST because, we need to know how much we're going to chop off the edges of the sensors and where all these artifacts might be so that we can correct for it. And so that's what we've been studying in the laboratory with this very precise setup. And we've got simulations of this is what the CCD looks like at the very edge. You can see all sorts of miniature electronics, and there's a pixel right there in the box at the bottom. That's 10 microns across. So you can see this whole image here is, maybe a couple hundred microns or something like that. Not all that much bigger than a human hair. The human hair can mess up this sort of thing terribly. So it has to be very clean. But we simulate this in computer simulations. We simulate the way that light and electrons may enter our CCDs and then try to understand them so that we can use all of the beautiful data that the LSST will collect. And so we've got knobs in a simulation, knobs on a camera. We've turned them both and watch how they interact and match them up to the models. It's been very successful. And one interesting thing that we've been able to do is look at those tree rings in not in terms of light, but in terms of how they shift stars. And so we project stars onto it, move them around, and measure the distortion of the stars on the CCD. And so you can see these little tiny faint arcs that were inside of the flat images are actually distorting the images of stars. And so this is the kind of precision. It's a 1,000th of a pixel of resolution that we're looking at. So it's a 10,000th of a micron that we have resolution to detect. And that's the kind of resolution that the LSST will have. So we have to be considerate of all that. And here's a whole page of the things that we've identified and we were measuring very precisely. And then all of a sudden, Starlink happened. So that was all kind of the backstory. You don't have to read any of the stuff that's on here. It's just scientific nonsense. But Starlink happened, and we I kind of at least redeployed my efforts into understanding what these bright, shiny satellites will do to our LSST CCDs. So it's a kind of a natural extension of what we were studying before, but now it's looking at how these bright guys, these are all stacked up satellites, Starlinks. There's 60 of them in each launch. They're like the size of a desktop, like the width of a table, and they just fling them out into space. And it'll give us all internet, but it'll also give us all a headache in terms of our astronomical imaging from amateurs all the way up to professionals. So it's something that we need to come to terms with and see how we can make the best of it. So as I was saying, we had that nice beam simulator in Davis, and the first batch of 60 Starlink satellites was just about a year ago, which is hard to believe because it seems like it's been forever. Time seems to be going pretty slowly, but at least for me around here. But yeah, so the Starlinks launched. Astro Twitter, which explodes. Amateur astronomers are really big on Twitter, and they started taking pictures of these things, and it became a big PR nightmare for SpaceX, which is a good thing, So that's a lesson to all of the astronomers and amateurs out there, is that you can make a big difference by just, kind of naming and shaming. If you want to, absolutely take a picture of these things, you can with your backyard camera, with just a DSLR. Sometimes if your cell phone, if you use a different app, you can get images of these things. There's tracks and trains, flying over at all times of the night. So feel free to take an image of it and upload it to Twitter and tag Elon Musk and say, hey dude, this is messing up my sky. And, things get done that way. So But yeah, so there was Astro Twitter exploded. This happened on the weekend, Memorial Day holiday. Next week, we're like, we got to check out what's going to happen here. This all came as a surprise. The brightness of these satellites was actually a surprise to everybody involved, including the astronomers and the physicists and the people who made the satellites. So it's been a really interesting saga over the past year, how people have interacted with this new phenomenon in the sky. And so in 2019, in November, the Dark Energy camera observed these Starlink satellites. And so you can see that on the right here, we've got images of streaks. And that's what happens in the CCD or in the telescope's images whenever a satellite goes through them. It's, if the satellite is going at, a couple of degrees per second, it's going to cross the LSST focal plane and under an exposure time. And so it just leaves a giant streak in our image. That's the residue of it. And so this is what it looks like in the Dark Energy camera, which is one of the largest cameras on Earth right now. You can perhaps see little segments inside of this image where those are individual CCDs, and the LSST will be around 10 times larger than this. And actually, I hope this works, but I'm going to pull up that image, which you can download for free on the internet. And this program called DS9, which is for Deep Space Nine, is Star Trek nerd made this program, obviously, but it's something that we use on a daily basis inside of the camera team. So this is the image. Actually, let me just zoom to fit first. I hope you guys can see my screen, right?
Yep, still good.
Okay, cool. There we go. Zoom to fit. So you can see this is the whole focal plane. I think it's like 500 megapixels or something like that of high-grade scientific sensors. And a Starlink train went right through all of these. And so this image has been actually propagated pretty widely. So some of you may have seen it. But just zooming in on some of the features, I think is really fun and might be fun for you guys. It's fun for me, so it might be fun for you guys too. But let's just take a look real quick at what these streaks look like on a small level, and what a raw image from a telescope might look like. And so you can see there's this segmented structure. These are all the different CCDs and different amplifiers, which have different gains. And so you need to correct for all of these differences between sensors. And that's part of what we're studying with the LSST. But you can also see a bunch of stars and galaxies in the background. And so it's just a really beautiful thing. But here we are with these gigantic lines going through the image. And obviously it's not the best thing ever. Let me just grab my little cutie here for a second. All right. I hope she does better up here. Okay, Leona. Say hi to everybody. Okay, so yeah, so it leaves these giant streaks through the images, and that's what we were doing with our tests here that you can see. So we had streaks of different intensities, brightnesses, trying to simulate a whole range of phenomenon and at different orientations and locations. And we actually learned a whole bunch about the CCDs, more than we ever expected. And so that's just a nice lesson, is that whenever you try something new, you often learn something new. And that's what we found with simulating Starlink streaks. And so we found an interesting non-linearity in the crosstalk of the camera, which was not actually discovered before this, but it actually turns out it might be an important thing to consider when we deal with these Starlink streaks in our data. And so the non-linearity of crosstalk, as I mentioned, crosstalk, some of you are probably familiar with, but not all. So it's worth saying that these, so you can see there's a main streak going from the upper right to the lower left here, simulating the main streak of the satellite. And then there's these secondary streaks off, secondary and tertiary and more off to the side of it. And these are just a fact of life, actually, for the CCD. We knew about the crosstalk that happens in CCDs that kind of creates these electronic ghosts of the main streak, but we didn't know that they were going to behave so wildly. And so there was a lot of study that went on with studying the intensity of these electronic ghosts, the amplitude of those with respect to the main streak, and we kind of tried to fully characterize the impact of these Starlink streaks using a variety of different methods. So all these results were from the UC Davis Beam Simulator. Now I kind of carried that work over to SLAC. And so you can see, as Boyd was saying earlier, these rafts they're the main feature of the LSST camera. Main feature size is these rafts, and it's a 3x3 grid of 4,000 by 4,000 pixels. So each of these squares is a 16 megapixel high precision camera. And so what we did to simulate this on the raft of CCDs the first time, because we didn't have the whole optical setup that we had in Davis at Stanford, we just took a pin laser and just went zoop right across all the CCDs as kind of steadily and smoothly, but also quickly as we could. You don't want to sit there with a laser pointer shining on this very expensive $1 million device. So you just went zoop like that, and I actually got a fairly straight line through there. I was very impressed with that. But that's that's kind of first pass at science that always happens in the laboratory when you're doing hands-on science. We also tried projecting little slits onto the sensors as we do in Davis, but it ended up with a sausage, and that's not really an interesting phenomenon. I mean, maybe an airplane would probably look like that if it flew through the sensor, but I think actually an airplane would blow out the entire focal plane. You'd never see anything, but yeah, so that was a little failed path. We also tried mounting a laser on a little motion platform and then stepping it through. That worked pretty well, but we ended up with a kind of jagged path because we weren't able to move an X and Y in the same way at the same time, and so that didn't really work very well. But we were able to get some really cool data, some cool images of the crosstalk that I was talking about, and what we observed in Davis, we now observed at SLAC at Stanford with the actual sensors that will go into the LSST focal plane. So we're kind of reconfirming the results that we had before, and the best results that we've had come from projecting this tiny little slit onto our CCD. And so we put that into a DSLR lens behind it and shine some light through it and project it onto the CCD. And this is what it looks like if you just look down the barrel of it. And that's what it looks like on those 9 CCDs. So we just kind of plop those around and take a bunch of data and then analyze that data. Here's some images of what it looks like on our CCDs. You can see various different artifacts that present themselves that need to be corrected. So I've been doing a lot of work on how to correct all of these crosstalk images, and it takes a lot of coding and things like that. So yeah, so we got a lot of data. We made a lot of plots, made a lot of figures. This is the crosstalk matrix, to use the jargon. It's just the way that all of the different channels of the CCD, there's 16 different channels with 16 different amplifiers in one little camera element, and they all interact with each other differently. And so we make this plot of channel versus channel, and how each channel interacts with another, and that's the crosstalk matrix. I think my wife just got home, so she can take the baby. Hooray! So she's being very good. Anyways, yeah, some more plots. We made tons of plots, like plots out the wazoo, and all sorts of cool sciences going on in here. But one of the key things that came out of this whole work is collaboration with SpaceX. So you can see here, we've got a draft paper with my advisor, some LSST people, myself, and then these 2 fellows from SpaceX in Redmond, California, Redmond, Washington, Hawthorne, California. We got SpaceX guys who are now part of the loop, and they're providing us information with the brightness of the satellites from different angles, and they're helping to darken their own satellites for us before they launch them. But the ultimate solution, the best possible solution, is for them to mitigate their own brightness in orbit. Of course, we can correct the data as we get it, and we're probably going to have to deal with some of that. But if they can actually dim these enough, maybe they won't be such a big problem. And so the sunglasses on top of the satellite here is kind of a little metaphor for what their best solution yet might be. And it's some of you may have heard, there was a press release about 2 weeks ago with this new concept called VisorSat, where the satellites are launched in this stack configuration, and then they decouple, they all spread out in orbit, and then this little visor flips up, just like the visor on your car to shield your eyes. It will shield the reflection from the bottom of the telescope from the ground. So it'll flip down and hopefully block most or all of that light that's coming off of the satellite. And so I think LSST will still be able to see these satellites because it's such a large telescope. But if they're not super bright, it would be the best possible case, the best possible outcome for this massive constellation of satellites that's going up right now. So yeah, that's the end of my presentation here. We can take questions. I can go through slides. I can show more pictures. I can show like this is how we're working on this paper with the SpaceX people. Since we're all not in the same location, we work on a paper. This is how it's been for authors for a while. You work on a paper all together on one website. So you just got a paper with all the code on the left and the output on the right, and this is how science proceeds these days. Just sharing kind of what I'm working on right now. Just a little view into my life and how we work and things like that. So, anyways, I'll definitely be open for any questions if people have them. Just shoot. So thank you.
Thank you very much, Andrew. Do you want to take your screen share off and then we can see?
Yeah.
I think maybe you'll be asked to put it back on again. So thank you, Andrew. Thank you, Boyd. Is Boyd back with us? Boyd is there. Yep, great. Thank you both for your contributions. There's a residual question earlier on from Martin Kessel about the exposure. Martin, can you speak to us? Or are you still with us? Martin was asking, each of your exposures is 2 times 15 seconds, but you have 5 filters on the cameras. So does that mean there's 2 times 15 seconds times 5 images for each, or 2 times 15 times 5 exposures for each area of the sky?
No, not necessarily. Sometimes that will happen. In some fields, I think there might be a filter change, but the filter change takes some amount of time. And the best thing to do when you have time that needs to be taken is to go to a different location in the sky. And so the way that the schedule is currently being simulated, it's not a final schedule yet. There will be a lot of on-the-fly adjustments, of course, that will happen, but it seems to be more efficient to do a large area in one filter, perhaps hours or an entire evening devoted to one filter, and then you can change your filter and do a different survey, do that same area later, like in the week or something like that. But yeah, so no, we won't have color images of each region of the sky necessarily every night, but every week or so, there will be a complete color image of the sky that the LSST will have.
Thank you. You say other guys at SpaceX been helpful to you? Where does the pressure come on them to put the sunglasses on their satellites?
They have been very helpful. That Elon Musk has said a lot of different things online. He was initially very dismissive of the whole issue and suggested we launch our entire observatory into space. And he's got these wild ideas. Perhaps that is a solution. If he wants to launch our observatory, launch the LSST camera, all the optics. It's not necessarily feasible to launch the entire telescope because that capability doesn't exist. But long term, that will be actually a solution, I believe. But in the meantime, yes, they've been very helpful. Actually, like I was saying that in showing the collaboration that they're putting boots on the ground with this issue. They're working on solutions. The pressure is coming from all of you, from all the people who complain online about this terrible problem. So keep up the good work. And hopefully there will be some regulation in terms of international agreements that things can't be, bright enough for the eye to see, so it doesn't spoil it for at least the average people. So yeah, it's an ongoing project. They've been surprisingly helpful so far.
Will they be able to, or will they need to retrofit sunglasses to the satellites that are already up there?
There will not be a need to do that necessarily. I think there's a couple hundred up right now, but their lifetime, their shelf life is just a couple of years, maybe 5 years at max. And so yes, those will be a problem, but really the issue is the tens of thousands to come. You know, in a couple of years, these things will be launching every week, and they'll also be deorbiting, you know, every week. So they're kind of it's kind of like a constant replenishment, but they have a shelf life of about 5 years. So the current brightness, really bright ones, won't be up for all that much longer, hopefully.
Is Tom there? Did you want to ask a question? Tom McNamara, rather than me reading your question out.
Okay, yeah, that's fair enough. So if I understand correctly, the main issue with the Starlink is obviously their albedo plus the fact that they're in low Earth orbit. At what altitude do they need to get to cause no more issue than the currently existing satellites? And also, do the current Iridium satellites cause an issue or not?
Yeah, that's a good question. Yeah, one of the largest issues with them is the fact that they are in a low Earth orbit. So they're a lot closer and therefore a lot brighter when they reflect. These satellites are also very bright. The way that satellites cool themselves is kind of passively in most cases, and the brighter it can be, the less heat that it has. And wild dogs out here. Yeah, so so some of them are planned to be at higher orbits, and actually those can be a problem as well because they're orbiting. Apparently, they're orbiting a lot slower, and so they'll leave a larger imprint on each image. But also because they're up so high, they'll be shining later into the night. They won't enter Earth's shadow for more than just a couple of hours. In some cases, they'll be in Earth's shadow, so they'll be shining almost all night long, especially during the summer. And so yeah.
Do the current geostationary satellites also pose a bit of an issue, ironically, because they don't block out the stars?
They do occasionally pose an issue to observatories. Sometimes they'll just destroy an image depending on what's reflecting. There's like old rocket parts up there and space trash and things like that. But there's only a couple thousand satellites distributed across 40,000 degrees on the sky, and most telescopes see under a degree or so. So there's this very small chance currently of a satellite going through the field of view. So it's a very minor problem for most observatories. But once you get to the LSST with its wide field of view, looking all the time everywhere in the sky, that's where the largest impact will be. And so that's what we're studying.
There's another question from Uncle Martin Kessel, who has neither a video nor microphone. I think he's asking, are there other operators? He believes there are plans for other operators to launch this type of constellation. Will you now be working with them to try and get their sunglasses on before they launch?
I think so there will be lots of other companies like Amazon is thinking of launching them. There's other satellite internet companies that are already out there, but the SpaceX was the first to kind of get their stuff up there. And so in the next 5 to 10 years, there will be probably tens of thousands of satellites up there providing various different services and things like that. So our hope is that the lessons learned from the SpaceX Starlink satellites being so bright and so obtrusive to everybody's lives that they'll want to dim them. But the hope is also to have just some international regulation on how bright things can be that you launch up there. And I think that's it.
Louise was raising some questions about who owns space and who permits SpaceX or Google or whoever else may be interested to put their satellites into orbit to have adverse effects on yourselves and perhaps other researchers from other nationalities?
Space is supposed to be everybody's. That's kind of the thing. There is no, there's not a lot of regulation out there. There's some agreements that you're not supposed to put like weapons up there, but yeah, it's and so for the U.S. There is the Federal Communications Commission that regulates the launching and the operation of the satellites because they communicate with Earth, I suppose. But yeah, I mean, there's all sorts of people that can weigh in and on this and kind of do some regulation. But yeah, I think it's going to be a fact of life, and it just came on very suddenly. But yeah, it'll just be part of the new normal that we're all getting used to.
Well, it's given you a job for a year, for a good few years.
Yeah. Oh, it's been a fun thing to work on. Yeah.
Will it get to the stage that their sunglasses have negated quite a lot of the work that you've been doing, or negated the need for the work you've been doing?
Hopefully, yeah. You know, I don't want to work on this for much longer. I got a whole lot of other things that I could be working on right now. But I think that at some level, the LSST will have streaking events in every image once it starts operating in a couple of years. So hopefully we've got it all under control and everything's going in the right direction at that point.
So, Kevin, did you want to ask a question about the deorbiting?
Yeah, I was just thinking with the number of satellites in the chains from Starlink, I assume that deorbiting them could give you the same, or if not worse, streaking effects as they burn up in the atmosphere, rather than just simply reflecting.
Yeah, that would be a problem for sure. I mean, but hopefully, I think that they deorbit them over like the South Pacific or something like that. So for the brief period of time that they're like going supersonic through the atmosphere and burning up, hopefully that's not over the observatory, but that would certainly ruin things.
That's what I was thinking, because the orbit path seemed to move across the whole globe because that's what they're designed to do. So yeah. I assume they have to choose their deorbit position.
Yeah, that's one of the nice things about them is that they actually have complete control over them with thrusters and things like that. That they'll be able to do a controlled deorbit of these things, so it's not going to land on anybody's head.
Will it be the case that Starlink satellites will be in your field of view all the time, a tenth of the time, 1% of the time, or?
It's a prediction that at least the Starlinks themselves, there will be about one in every image. So there's ongoing efforts to kind of dodge them, perhaps, but that kind of takes a hit on the efficiency of the survey. You kind of want to have, you don't want to move the telescope if you don't have to. So yeah, there will be about one Starlink in each image, and if there are multiple constellations of, Amazon and Samsung and Apple and whatever else decides to launch their stuff up there, all sorts of international companies. Yeah, there could be more, but if we can get rid of the crosstalk effect in particular, which has that multiplicative, one streak turns into 20 in various different locations. If we can get rid of that multiplicative effect and just delete the streak itself, there won't be that much of an impact on the LSST survey, because that's one of the features of the survey is that it takes multiple images of the same piece of the sky. And so you build up a stack of hundreds of images and only one or two of them have a streak through it. You can just delete it and average out the rest of it. So it's kind of built into the survey how to deal with transient phenomenon like this.
So you said you could move your telescope to avoid seeing them. Could they move their satellites to avoid going through your view?
Yeah, that's
Black
one
hole of Chile.
That has been floated. That's an idea. Since they have active control of the surfaces, they can orient them so that they're not shining down. I think that might be a little less feasible than just by default darkening them, because not all satellites will be controlled, but if you can just have a passive darkening method, that I think would be a better long-term solution.
Thank you. I wonder if anyone else wants to. I seem to be asking. I'm asking questions for other people, asking questions for myself as well. Tom, did you want to add something as well? Tom McNamara? Is Tom there?
Hello, yes, sorry. I'm sure it probably wouldn't be an improvement, but could you use the fact that the Starlinks are going overhead rather than a laser for the adaptive optics, or would that not really be an improvement on the current system?
Are you talking about using the streak itself to calibrate the optics?
Yes.
Yeah. Oh, I'm so into that. Yeah, I love that you brought that up, because yeah, it's actually kind of a remarkable situation. In the same way that we learned a lot about our sensors from simulating the effect on them, we learned all sorts of physics about how the camera and its electronics work. I think that perhaps it could be a good way to calibrate the instrument somehow. You know, for instance, the streak. It's usually a very straight line, and so you can kind of measure how the focal plane is behaving in terms of spatially. So that might be nice. It might tell you how the atmosphere is distorting it. If you know that it's a single source very high up in the sky, just a dot, perfect, you know, almost as sharp as a star, but not quite, because it's actually slightly out of focus relative to the stars. So a slightly out of focus dot moving across your focal plane, you could imagine using that to calibrate out the atmosphere or something like that. So we could turn this into a positive. I think there's a lot of study that needs to still be done as to whether or not we can do that. But yeah, totally. Thank you.
You wouldn't necessarily want to tell Elon Musk that, though.
No, exactly. We're not gonna thank him for putting satellites in our field of view.
Carolyn, did you want to ask a question about Starlink still being visible?
Yeah, I really love watching Starlink, I'm afraid. I just wondered if we'd still see them once the sunglasses are on.
By eye, no. By eye, it should be dark enough to avoid being seen by eye. But in camera exposure, maybe a telescope, you might need a telescope to see the visor darkened ones. Yeah, sorry. It's I know it is actually a remarkable time to go see these things, because they're quite impressive, these trains of satellites moving across the sky. I know you guys have a fantastic view right after launch. Usually, if the timing is right, from Florida, they go right over the UK, and people see these UFO-looking things, and I'm so jealous. I wish I could.
It's amazing. It's truly amazing when you spot them. I mean, I go out every night to look for these things when I've got a tracker.
Yeah.
We very rarely see them. The last few days, the skies have been extremely clear. That hasn't been too bad. But once traffic starts going again, I think we probably won't be able to see them so easily in Manchester.
Yeah. So see them while you still can. Hopefully they'll be invisible soon.
I think it's 10:23 going over tonight. Not sure, something like that.
Yeah, usually before 10. Yeah.
10:23.
Yeah, go check it out, people. Take pictures and post them to Twitter and tag Elon Musk.
Yeah, but that would be one of someone from the astronomy community being pleased with his satellites being up there.
Yeah.
Post the picture. Don't want to see these. They're obscuring my stars.
Yeah, get them out of there.
So, does anyone else want to ask any questions of either Andrew or of Boyd? Before I think Andrew, Boyd, thank you so much. This has been for me, sat from my study at home, and I hope for everyone else in South Manchester. It's been, or elsewhere in the country. I don't know where. I'm not sure that I know everyone is in South Manchester. I recognise most faces in the gallery view. I think this has been a remarkable achievement in very difficult global circumstances. But the technology has been, for me, for this talk, has been tremendous. So I would like to thank you both very much for giving of your time, your daytime. It's a